Okay, so let's continue. So the next topic for this week is map projections, or the coordinate reference systems, more importantly. And as shortly mentioned already during the last tutorials, this CRS information, or the coordinate reference system information, is crucial because without that information, the geometries that you have or the collection of coordinates, they are simply kind of coordinates in arbitrary space. So you are not associating that into any specific area, or you might be, but the one who is actually using the data might not know what is the kind of space that you are linking it with. So basically the coordinate reference system tells for Python how those coordinates are related to different spaces on Earth. And that's of course a crucial thing in GIS. So it's quite an important aspect to grasp. And there are hundreds of different coordinate or the projections and coordinate reference systems that you can choose from. And here we see a couple of different ones. This is from this kind of comic, which is actually quite cool. But this Robinson projection is, for example, quite a popular one when presenting some data on a global level. The ones, for example, that Google unfortunately have used is called Web Mercator, which really this kind of the sizes of, for example, different areas get really incorrectly there in Web Mercator. Let's take a look at this map projection. So this is quite fun. Kind of a comic telling what the projection you use actually tells about yourself. So as Mercator here indicates, well, you're not really into maps. Basically, as we can see, so the kind of Greenland is bigger than South America and so on, so it gets really wrong idea of the world. And unfortunately Google, which is kind of a standard what people actually see when they are using maps, has been using extensively this Web Mercator projection, which is a bit different than this one, but basically have similar features. Luckily nowadays, if you zoom out with Google Maps, you actually get a globe in 3D, which is a really good improvement, but it was more than 10 years kind of this 2D image of the world. And basically when we are talking about map projections, what we are doing there is that as our globe is a kind of round object or geoid, so there is kind of no correct way of representing that 3D space into two-dimensional space, because no matter what we do, certain aspects of the map that we will do, or the coordinates, are always somehow incorrectly represented, because of it's not possible basically to really in a good manner to represent the three-dimensional space in 2D. But of course there are a lot of different ways how these things can be handled, and so that we can correct, for example, the kind of, well, the Mercator is basically where the directions are always correct, but for example the areas of the different continents are really not in correct sizes. And then there are, for example, this Robinson is kind of a it's fairly okay in many respects, but not really good at any. So there are kind of drawbacks in each one of these. Then we have these really weird ones, like this Dimexian that, yeah, it looks like some Power Ranger logo or something, but But yeah, so as we can see already from here, there are a lot of different ones, different projections, and these are quite funny, these descriptions, what these tell about you. So I like this Robinson, so I seem to have comfortable pair of running shoes that I wear everywhere. I like coffee, I do, and I have actually nice pair of running shoes as well. I enjoy Beetles, so yes, correct. You think the Robinson is the best looking projection, hands down. So yeah, so this is fairly nice as well, but of course there are many others that are good in different aspects. So what we will do in this tutorial now is that we will kind of take a look a bit deeper how we can define those projections, what kind of projections they are available, how we can find information about different available projections and so on. So that's kind of the aim for these. Yeah, by the way, well, this comic was really nice and funny, but there are also more maybe kind of more scientific resources as well linked in the materials. So this georeference.org, so this has a kind of a good information about the basic properties of different projections, why they are, when they should be used, and so on. Then there is this other blog post in here that actually, which is pretty nice because it kind of represents information about why certain projection is good, what are the strengths and what are the weaknesses of different projections. And it has nice illustrations what actually happens if we try to draw, for example, a circle using a specific projection and how it distorts in different areas and so on. So take a look at those links if you're interested. I recommend to take a look at those so that you can get a bit of more understanding of the availability of different ones. But let's start actually seeing a few examples how we can define to transformation, so reproject from one coordinate reference system to another in GeoPandas, which is really typical procedure to do. So in this lesson 2 data, or the directory that we downloaded, so as I mentioned, we have also this Europe borders in there. So that will be the data that we will be using. And let's again start by reading the data from into pandas from the directory. So let's again import GeoPandas as GBD. Then what we want to do is that we want to read that file. So the file that we are going to read is located in L2 data directory, and there we have a shapefile called Europe borders.shape. During this we are only going to read data from shapefiles, but during the upcoming weeks we will see how to read data from different file formats that you can actually see how that can be done, if you were wondering. And now let's again read the data into a variable called data, and we use again this gbd.read file, and there we say that we want to read this file located in this directory, and let's do that. No kernel, okay. If this happens, you need to click that one and then press select, and after this, hopefully, yes, things are working. Again, there is this warning, but don't worry about it. It shouldn't affect anything. Let's just first print the head so that we can see that, okay, in this file we seem to have some polygon information in here, and then we have this variable called TZ ID, which is time zone ID for each polygon. But what we are really interested in here is that the CRS, so data.crs, and when we call that one, we can see that, okay, this is quite familiar from last tutorial, where we saw that, okay, we have this Python dictionary, we have this keyword in it, and then we have the EPSG information in here. So from here we can see that the coordinate reference system seems to be in this European Petroleum Survey Group 4326 code. So there is information in this link more about the EPSG dataset and the codes if you're interested in. This is a standard, I believe, created for the oil industry when they have ships traveling around the world, so they somehow initialize this thing. But it doesn't matter, that's kind of the source of the code, EPSG. But basically what it has is, indeed, as I mentioned earlier, it has a lot of different kind of codes representing different coordinate reference systems. This is widely used in QGIS, in different GIS softwares as well. There is a lot of information available for different spatial or the coordinate reference systems. For example, the spatialreference.org is a good source. So basically here you can, if you are, for example, I have been, it seems, interested in Eurofin, which is the Finnish standard coordinate reference system, so you can basically look for it and it doesn't find anything. Let's say ETRS. So basically here you can find information about different coordinate reference systems. Let's call Finland. Let's see if we have something there. So if I, for example, look for Finland, so then I can see that there are various different coordinate reference systems that might be useful for Finland. For example, let's see, do we have, these are actually fairly old ones. But anyway, so WGS, there is a lot of coordinate reference system having that one in there. We have Mercator in here. That is kind of associated to many. But anyway, so this is a good site to look for different coordinate reference systems. Then we have this proi4.org that is also a good source for having a bit more information about how these coordinate reference systems actually work and how they map the spherical 3D space to a flat 2D space, as it says in here. What we are going to use, for example, today is this Azimuthal equidistant projection that looks something like this. So what kind of qualities or characteristics this projection has is that when you use this projection, you specify certain kind of center point, and then the distances from that point to any direction will be correct. So it has this kind of special character, this one. But there is a lot of information about different, such as Eckert for example. So we can see that this is this kind of global projection looking like this. So it's a good source of data. And then third one is this MapRef, where there is some information about the CRSs in Europe, for example, in different countries, so this might be useful source of information as well. Good. But let's continue from this quick introduction to the different resources available on the web to actually take a look at what does our data look like. So let's take a look at the geometries, how do they look like, and we can see that again we have some polygons in here, and we have coordinates, and these look like latitude and longitude coordinates, but without this information we wouldn't be sure, but because this has the coordinate reference system defined, we can be certain that this is actually WGS coordinate reference system. Are you familiar with WGS coordinate? Yes, good. That's really basic coordinate reference system. Basically all the GPS data, for example, will be most typically in that that coordinate reference system and so on. But let's do so that one really typical thing that you want to do is that, for example, when you want to do some comparisons between layers, to, for example, select certain points that are within certain country, for example, in this case, as we are having the European borders in here. So the really key thing there, before you can actually do any selections, is that those coordinates need to be in the same coordinate reference system. Because if we would, for example, compare the latitude and longitudes to some metric projection, of course those won't never match. So one of the really typical things to start with when doing spatial analysis with Python is that you need to ensure that all the data are having the same projection, or the CRS. So let's see how we can do that. So what we want to do is that we want to reproject these European border data from this WGS84 projection to this Lambert Azimuthal equal area projection that has this EPSG 3035 code. And why do we use this one? Well, it's the one recommended by the European Commission, so that is actually the projection that whatever map you are going to see from EU, that is the projection that they are using. So probably when having some countries from EU or Europe, that is a good one to use. Of course we could use whatever we want, but that's one kind of criteria what we could think about or consider. So let's start by making a copy of our original data. So indeed we read the data into this data variable. So let's create a copy and called orig, like original data. And how we can create a copy of a certain data frame or geodata frame is that we can call data.copy. Fairly intuitive. And now what we want to do is that we want to reproject our data into EPSG 3035, the one that we was mentioning here. And luckily that's really easy to do in GeoPandas. So again, what we need to do is that we say that we will store this projection, we will basically update the data geodata frame that we have. So we call data equals to, and then what we will store into that one is the data. And then how do we do the projection or the transformation is that we have this function called data.toCRS. And what this function takes as an input parameter is basically, well, you have two options. You can pass in the there's EPGS, it should be EPSG code or CRS string. We will see that later. But now, as we know that we have this EPSG code, so we can specify that EPSG equals to 3035. And now let's print out the data, geometry, and let's print out the first 5 rows after doing this projection to see what happens. So now, as we can see, so what happened was that the coordinates in our polygons changed. So now we seem to have something large numbers, which is due to the fact that they are now projected into metric system. So now they're not on the 3D kind of surface locations, but now we have them on metric system in 2D. And we can see the difference. So this is the original one. So indeed, here we have the latitude and longitude values, and here the metric systems. But of course, the best way of actually seeing what happens is that we create maps out of them and actually compare. So let's create 2 maps side by side, one representing the WGS map and the other one the new projected map or the data that we have. And we will use the matplotlib again to do that. So we want to import matplotlib.pyplot as PLT. So this is something that we used a lot in the exercise 7, for example, last period. And now what we want to do is that we want to make subplots. So we want to make 2 plots that are next to each other. And it is something that you practiced in the exercise 7, and I heard some rumors that it might have been a bit challenging for someone. So let's go through that procedure once more, so that you, and if you have questions about that, so you are free to do so. But what we want to do is that we want to make subplots that are next to each other. So in the exercise 7 we wanted to make 4 plots that we have 2 rows and 2 columns. Now what we want to do is that we only want to have 2 columns and 1 row, so that those 2 are next to each other. So we can use this plt.subplots to do that. So what that function actually returns is that it returns the figure or the canvas that we are using to draw the map. Then what it does is that if we, well, maybe before going here, I specify the plt subplots, and this is the one how you can actually draw or create multiple axes for the plot. So we specify that the number of rows in our figure will be 1, but the number of columns, n-cols, will be 2. And then we can specify that the figure size of our figure, let's make it a bit bigger than it would be, is 12 inches by 8 inches. So it's a bit wider than higher. So this is the function how we can create subplots with 2 columns, 1 row, and what it will return is, first of all, it will return the figure having all of these axes, and then the other thing it will return is a list of 2 axes, because we have 2 columns defining here. So we will have two axes, one representing the left one, and the one representing the right axis in our figure. We could do it like this. So we can say the fig and axis, and then this variable would have both of those axes inside a list. But there is a trick actually to do it in a way that we don't need to have a separate function or separate commands like this. x1 equals to axis 0, x2 equals to axis 1. This is probably the way how you did it in the exercise 7, and this is how we showed it to you. But there is kind of a shortcut of doing this. So instead of writing 3 lines of code, we can basically do these steps already when defining this. And how we can do it is that we specify it like this. This is now a kind of, it doesn't matter which one you use, this is kind of a trick, good trick to know. We can do it like this. So inside these parentheses, because we only have 2 columns and 1 row, so it will return a 1 list of items. So we can take those items from that list by doing it like this. So inside the parentheses, you specify that the x1 variable will have the left plot, and the x2 will have the right plot. You could also specify x3 if you would specify the number of columns to be 3 and so on. But because we have 2, we will do it like this. So this is just a trick to know. And what we are going to do is that we will plot the WGS map on the left one, so to the x1 column, and then the Lambert azimuthal equal area projection to the right one. So let's plot the WGS 84 Geodataframe to x1. And how we can do that? So the WGS 84 is now stored in this variable orig that we copied in this step. So let's call that orig.plot, and inside this plot function we can specify that to which axis do I want to plot this. With this parameter called x, we can specify that this plot should go to this x1 subplot that we have. And let's say that the face color, so the color of the polygons that we have, will be gray. And well, we can try this out already now. So what happened here? Well, now we can see that indeed now we have a gray European borders in here, and on the right one we don't yet have anything because we didn't plot. So let's plot the other map into this right one in here. So now plot the ETRS LAEA, so Lambert azimuthal equal area projection. So this is now stored in our data Geodataframe. So we call data.plot, and this will be stored now in this x2. So x equals to x2, we'll now store it to the right one in here. And let's change the face color to blue. And now we can see that, okay, now we have this the projected one in here, and what we can already see from here is that they look quite different. So as we can see from the coordinates, well, these are the latitude and longitude values and we can see that the countries are more or less a bit stretched. The norther we go, the more kind of incorrect the countries start to look like. But with this equal area Lambert Azimuthal projection, the country sizes are more or less should be correct, and it looks better. Let's make a couple of more additions to make these maps even better. So we can say that let's add titles. So let's add title to the ORIC one. So the X1, so this one, let's add title called set title WGS A4, and let's set the title to the other one. So X2 dot set title ETRS Lambert Azimuthal equal area projection. And then there is a trick to remove empty space or white space around the plots. So plt.tight layout. This is a trick to remove some extra space. Well, there is not much, but let's see if this does some changes in this one. So now we can see that we have the titles in here, and we indeed seem to have quite different looking maps. And whenever doing visualization, for example in Europe, this is a good one to use because the countries look more or less correct, and the sizes of the countries are kind of representative, and they can be compared to each other. Good. So the key thing was a simple function called toCRS. So this is a way how we can actually transform and reproject data from one coordinate reference system to another. So fairly straightforward thing to do. So let's finally save this into shapefile again. So save to disk, and let's again call output fp l2 data Europe borders EPSG 3035 dot shape, and then data to file out fp. And doing this, now we should have have the file in here. Let's refresh this, take a look. Yes, here we have the Europe borders, and here we have the new one. And now we should have in this one new projection information looking like this. And it's different than the original one, as we can see from here, which is much simpler. It's just this WGS projection file in here. This is now a note for Windows users. In Windows, typically doing things like this, and when saving the file, for some reason or another, it's related to the FIONA package. It doesn't necessarily save the PRJ file, so the projection file. So I will now show you a really kind of secure way of doing this by using a certain package called PyCRS. This is a useful package anyways for all of you. So even though you would be using Linux or using the instances that we have, this is something that might be useful for you to see. So we can use this package called Pi CRS. There is actually, so there is a link to this. So what this package is good is that it's really good for kind of being able to convert between various common coordinate reference systems, as it says in here. And why this is so good is because it has the most extensive set of available coordinate reference systems available. For example, Esri has certain specific Esri codes, how they store their projection information, and with this package you are actually able to use also those Esri codes. So it's really good, and also many others. So basically it can store and represent the definitions including these different systems that are available. So this is a useful package to know. So yes.
I have a question. When I save the files, it is like 4 different versions of it, but with a different file text. So it's like 4 different. It's both DBF and PRJ. That's when you store it, you want to get 4 different versions.
Yes, and that's related to shapefile file format. Okay. So shapefile is always actually consisting of multiple different files. So that's kind of the minimal set that you need to have. So you need to have the .shp, so the shapefile that contains the geometric object, so nothing more than that. Then you have the dbf file that contains the attribute information, so the table that you are reading, so all that information is in the dbf file. Then you have the prj file that contains information about the projection, as we saw. And then the last thing, what is it? Then you have the shx file and the cpg file. I'm not actually. So the cpg file seem to be, I don't know, seem to be some kind of standard information about, let's see. Let's see if this tells us something. Esri code package file, so it's something related to the Esri files. Yeah, so probably nothing too important, and the shx file is something. Okay, it's something related to all the desks. So some files basically related to different software so that they can be used. Yeah, but the important files are basically, in terms of shape files, it's the PRJ and the DBF and the shape information. Good, but now as the timing's running, let's see how we can use this PyCRS package to define certain the CRS information as these kind of PROI4 strings. So that's a specific way of storing the coordinate reference system information in certain manner. I will quickly show you, or soon show you. So let's define. So indeed, if you're a Windows user, this might be the thing you need to do, because you might, the GeoPandas, or actually the Fiona package, might not correctly store the projection information. So define the projection. So let's create a variable called EPSG code, and that will be 3035. So this is the projection that we are using, that we defined in here. So it's the European projection. Then we can right away pass this information, this data.crs. So now we are updating directly these coordinate reference system of that geodata-frame. And how do we do that using this PyCRS package is that we can call PyCRS dot, and then it has a submodule called parser, and under here it has a function called from EPSG code. So quite similar that we saw at the end of the last tutorial, but not exactly the same. And now what it wants is that it wants to have the EPSG code as the number. Well, we stored it into this EPSG code variable, so we can pass that into here. And then after this, there is a function called toProj4. So this set of two different functions, we can actually specify the proj4 string into this data.crs, and we can see what does it actually do. And why it's like, yes. Okay, now, yeah, there is a wrong version of the, let's take a look at it from here. So what it basically, so this is now related to the environment, nothing to worry about. If it would work, and it will work later, it should print something like this. So this is a text representation of that coordinate reference system. So what we have here is that we basically have specified an ellipsoid, like the what is the kind of 3D model of the world that we are using to do the projection, and then we should have probably some data information as well, but then we have the information about what is the projection. So it's the LAEA, which is the Lambert Azimuthal equal area, so this is just the name of the projection, and then we have certain kind of parameters in here. So this might be a bit confusing to look at, but basically with this function you can create these kind of text representations that will be then stored accurately in here. And actually this does not look like the one that this is not the same as this one, but there are multiple different ways of defining these projection information, and this is what is the, is it WKT format, basically what is formed, but anyway, you don't need to worry about that too much. But anyway, it will store the information in correct manner into this file, and in on Windows this is something that you most probably want to do. Good. So now I will fix this into the environment later, but basically this should work, and it will work after some fixes, and then we can save that file on Windows, and it should work as well. Then as a last kind of example, let's see if what stuff do we have in here. Well, let's try to be quick. So as a last example, kind of a practical example, what we can do is that I mentioned already with this one, this Azimuthal equidistant projection. So there are kind of special projections that have certain characteristic, and this is one projection that indeed has the information about the distances from certain location correctly in each direction. So this is now, I believe this is now the EPSG, well, this is the Europe borders data that we just reprojected in that format. So now we can No, this is actually the final result. Yeah, so this is the final result of the after the reprojection, where we have Helsinki as the center point, and what we are interested in doing is that we want to calculate distances from other European countries to Helsinki. So basically, and how do we define the other country is the centroid of that country. So that's kind of the aim, what we will be doing next. And as we can see, the zero kind of location on these axes is located somewhere, well, exactly on top of Helsinki. And then if we go to the eastern part, the distances start to accumulate in meters. So they are plus something on the western part, they are minus something on the northern direction. They are again plus some, and to the south they are minus. So it kind of gives you information about the distance from certain locations. So let's take a quick look. You don't now need to follow. I will just do this fairly quickly so that we can get a third example of how we can do stuff. So let's first create a geodata frame that represents the Helsinki location at certain area. So we again use Shapely for doing that. So from shapely.geometry import point. And then the coordinates for Helsinki. So we specify that Helsinki, so HKI, longitude equals to 24.9417, and the Helsinki latitude coordinate equals to 60.1666. And now what we want to do is that we want to create a geodata frame based on these locations. So let's create geodata frame. And we can actually, with one line of code, we can create a geodata frame based on this information. And I will show you how to do that. So we will create a variable called Helsinki, and we will start by specifying the GBD geodata frame, and then we start passing information inside this geodata frame. The first information that we want to assign there is, of course, well, it's the geometry. So we will pass basically inside certain row and certain column. So basically we need to have two square brackets in here. And there, what we will do is that we will insert into that row and column a point. So it's the Shapely geometry point having the Helsinki longitude and Helsinki latitude as the coordinates. So in this way we can already create a geodata frame with some data already inside there. So the first parameter in this geodata frame is basically data, and it can be, for example, this kind of representation of the data. Then when creating geodata frame, you need to specify from which column the geometry information should be read. By default, it's always this geometry, as I mentioned. So we specify that geometry equals to geometry. Then important information with any geodata frames is the CRS. So we need to specify that the coordinate reference system of this data, well, these are latitude and longitude information. So we can specify, we can pass the coordinate reference system dictionary inside here. So as we saw already a couple of times, that when we print out the CRS, it prints out this kind of dictionary. But of course it works other way around as well. So we can basically create this dictionary and pass it to Geodataframe, and then we can specify that this coordinate reference system is EPSG 4326. So this is kind of how we can represent the WGS 84 projection. So now we have the necessary information defined to the Geodataframe, but the tricky thing is that we have defined this geometry that should be read from column geometry. But because we are just initializing our data frame, it doesn't yet have the name geometry or the column geometry. So we actually need to define that what are the column names in our Geodataframe when it's initialized. So there is a parameter called columns, and what this takes as an input is a list of column names that should be created when this Geodataframe is initialized. So there are a few steps in here, but basically this is a way how you can with one line create a Geodataframe using specific locations such as these coordinate points. And it will first create the column, then it will specify the geometry and the CRS and so on for the Helsinki. And now after this we can print what is Helsinki, and no kernel again. Let's print out kernel. Maybe I need to import GeoPandas as GPD as well. Yeah, and now what we can see when we print it out Helsinki, so now we have a column called geometry point there, and we can check what is the type of Helsinki. We can see that it's a Geodataframe, so everything is more or less in order. So now what we want to do is that we want to specify this a bit custom projection to this Geodataframe called this Azimuthal equidistant projection. It's not kind of a really special in that sense that it can be found from PyCRS and so on. But the fact that in this projection we have parameters that we can pass in. So what we want to pass into this coordinate reference system is that what is the center point? So where does this projection actually center itself to represent the correct distances to all other directions? So we want to specify that center point is located on top of Helsinki. And because that is a bit custom thing to do, so we need to use a package called PyProj, which is a wrapper around, so it's kind of Python package for this Proj4 kind of standard that is under the hood of many programming languages. So we use that to actually create this projection for ourselves. So we import this package called PyProj. It should work. Yes, it works. It should work. It's basically also under the hood of GeoPandas, so it should always work. And now we want to define the projection and center it to Helsinki. So let's create this AEQD, so aerial, what was it, Azimuthal equidistant projection. And what is this really? Well, we have, I mentioned already earlier, so this is the projection that we want to use. And And basically what this has, so this has certain parameters that we can actually change. So the ones that we are interested in is this lat underscore 0 and lon underscore 0. And it says that latitude of projection center and the longitude of projection center. So we want to actually update these values in our projection, and I will just show you how to do that. So we will create this kind of PyProi for string representation. So it's the text version of this projection information, and we will use this PyProi dot proi, which is kind of now we initialize our projection. And what is the projection that we want to use? We can pass this proi parameter into it, and we can take a look from here that the alias for this one is this AEQD. So we need to pass that information into here. AEQD is the projection that we want to use. And then we need to specify certain parameters, such as the ellipsoid. There is also more information about what is ellipsoid and what is datum and so on. I won't go into too much of details in those ones, but you can read more. And the ellipsoid will be the WGS-84 that represents the model of the Earth. And then the datum is the same, WGS-84. That is kind of the reference to the locations on Earth. And then what we want to update is exactly those lat 0 and lon 0 values to center out our projection. So we will just call lat 0 equals to, and where do we want to center it? Well, it's the Helsinki latitude. So we created in here the Helsinki Geodataframe. So we want to use those to actually, those coordinates to specify the center point for this. And this is what we have, and when we execute this, we can check what do we have now in this AEQG in here. We can see that we have this kind of object in here. So it's this pyproi.proi object located at certain memory storage in the computer. But there is this .CRS, so spatial reference system attribute that will actually give you this. So now what we have here is that we have the kind of text version of the projection that we can actually pass into our Geodataframe. And it's centered into this Helsinki location in here, and we should be okay to continue. So the last thing what we want to do, we want to create and reproject our map into this one. So let's again make a copy. So let's say that borders, Europe borders, AEQD equals to data.copy. So we just, oh, data is not defined. We need to because I lost the kernel, so I need to read it again like this. So now I should have the data. And now I take a copy of it. And then what I want to do is that I want to reproject this data. So now when we take a look at the data, we can see that, well, at this point the geometries are in the decimal degrees, and now we want to use our new projection that we just created to reproject our data. So we say that Europe borders underscore AEQD QD equals to the same name dot to CRS. And now instead of passing the EPSG code, what we are passing in here is actually the CRS. So CRS equal to this one that we created here. So we use this information to pass the CRS. So AEQD. So it will get this string format to do that. And when running that, and that's not defined because I didn't run it yet. So now I should have it. I have misspelled something. Yes, borders. Now, finally. Okay, and now we should have something in here differently. And as we can see, now we have these kind of metric coordinates in here. Finally, we can basically create a plot out of it. Europe borders plot to see how does it look like. And now I need to use the magic still. Matplotlib inline to actually show that. So this is what we get. So now our coordinates are centered around Helsinki and we have the distances. And we will now finish, but basically if you're interested you can continue to the latter part. And actually it's good to go through this tutorial and in the end, because we will see how to use apply function to calculate distance. So the latter part or the final parts of the tutorial will basically show you how to calculate distance from centroid of those countries to Helsinki, and you will receive that information and store it to certain variable. Unfortunately, we are running out of time, so don't have time to do that, but you can follow the tutorial to the end and reproduce the things. But basically, as you have now seen, depending a bit what is the projection that you're interested in, there are various ways of actually specifying and defining the projection. The one that we just last did, so using this Azimuthal equidistant, is quite not that commonly used. At least I don't use it. So it's pretty rare that you actually need to do something like this. Most often, for example, how I define the projections is that I either pass the information with these dictionaries or use this CRS parser to do it. But of course, because most often you have shapefiles ready that you are actually reading in, you have that information to start with. So you don't need to necessarily do any definitions when we are doing the data analysis. But what is important, and we will learn that later, is to specify that each data layer that you might have, for example, 3 shapefiles that you are reading in and then starting to do something with them. So the important thing is that they should be in the same projection. So you need to use this 2CRS to ensure that everything is on the same projection. Some common thing also is that if you have WGS 84, so latitude and longitude coordinates in your data, and you are interested in the distances, for example. So, well, decimal degree distances are not that useful most often. So quite often you want to reproject into some metric projection, and then you get more kind of that, okay, the distance between this and this point is 10 kilometers or 10,000 meters and so on. So those are kind of typical things. But yes, so I recommend you to go through the tutorial once more if you have time. And then we have the exercise 2, and there is the, in a similar manner, we practice the things that we learned today. So we will create a polygon from list of coordinates, so how to create geodata frames. We will read some data from some data file, and then we will basically create kind of geodata frame and shape file from a text file containing information about latitude and longitudes. So something really typical that you need to do, and the people who are not familiar with GIS, this is the question that they typically do and have, that I have this Excel file or text file with these coordinates, how do I make a map? So this is kind of that problem to do, how to do that in Python. And the third one is basically kind of going back to the examples that we saw. So calculate some distances and create line strings and so on. So that's it for this week.